Welcome back. We'll now cover Unit 2.3, Pressure of Gases. So we're going to talk about generalities about pressure of gases and how we measure that pressure. So pressure, first of all, is a force applied on a surface of specific area. So this is basically based on the amount of collisions that, for example, air has with a surface per unit, again, of area. The more collisions there are, the more particles of air will collide with a surface, the greater the pressure. So it's basically a sum of those little collisions. For example, if we have a soccer ball here, the more air particles are in a soccer ball, the more collisions there will be, obviously, between the air and the inside surface of the ball, and therefore the harder the ball will be. So you can think of a bunch of kids in a little inflatable playground, and they're running around and they're throwing themselves on the walls of that inflatable playground, and those would be the little air particles throwing themselves at the walls of the soccer ball, therefore stretching it outwards and giving it its shape, inflating it basically. So a question: if two gases are the same temperature, but one is heavy and the other one is light, which one would better inflate the balloon? Now, if you remember what I said in the last lesson, if they're at the same temperature, they basically have the same kinetic energy. So the only one thing that will change is the mass in this case. And that mass will influence the speed of the particles. So if one is heavy, it will travel at a slower rate, and if one is light, it'll travel faster. But in the end, they'll have the same amount of energy. So it's just a question of how fast or how slow the balloon will get inflated. And by the time it's inflated, it will stay inflated at that point because the gas will occupy all space available. So two equivalent containers, two equivalent balloons, one with a heavy gas, one with a light gas, will in the end be inflated the same way if they're at the same temperature. It's just that one will take longer to inflate than the other because of the nature of the gas, which is heavy or light, and therefore will influence at what speed those particles will diffuse through the balloon through translation and therefore inflate it. Okay, so that's basically what you have under this box here. So it's neither or both. Okay. Next, we have atmospheric pressure. So it's a gravitational force that keeps the atmosphere from escaping in the outer space. So we know that the atmosphere is made of air, of gases, right? And those particles are so light that if given the chance, they would just go in the outer space because there's nothing out there. It's basically a vacuum. There's very little particles traveling in there. So what's keeping those gas particles that form our atmosphere from escaping and going away, it's basically the gravity of the Earth. So again, that atmospheric pressure, because pressure is not illustrated but really created by collisions between air particles and a surface, the atmospheric pressure is again exerted by the air above us and the collisions of those particles on a given object or person. But the way we're going to measure it, we're going to basically look at a vertical column of air. So if somebody is standing, all the air above the person will represent the atmospheric pressure. Now, at higher altitudes, there's less air, right? So less collisions. And therefore, that's why also it's harder to breathe because there is less air, less oxygen. So because air is rarer, there are less collisions, and the pressure is therefore lower. What do we use to measure atmospheric pressure? Well, we use a barometer. Now, there's different types of units that we use. These days we use the kilopascal, but in the past they used to use millimeters of mercury. So they had something like this, which is a column of mercury. And so they would have an open container, and they would have a column whereby you'd find the mercury inside as well. And depending on the pressure of the atmosphere on this surface, it would push some mercury up the tube, or if the atmospheric pressure was lower, this would come down back into this section. So depending on the height of this tower, so to speak, well, they would be able to calculate roughly what the atmospheric pressure was. It's a little bit similar to what you had in one of the labs last week, where you were measuring the height of that colored water in the tube. Now, like I said, we're now using the kilopascal as a unit. They used to use millimeters of mercury because that's what they use in their device as a liquid. There's also atmospheres that we can use. Atmospheres are used mostly underwater. So for example, if you go diving or if you were to be in a submarine, this is the unit of pressure that water exerts on bodies. And then we have PSI, which is pound per square inch. We see that mostly in tires, so car tires, for example. We're going to work mostly with kilopascal, obviously, but because these have specific uses and they're still seen from time to time, it would be good to know these as well, these conversions. So 101.3 kilopascal, equivalent to 760 millimeters of mercury, which is equivalent to 1.00 atmosphere, and 14.7 psi, pound per square inch. Okay, so now I'm going to show you a little video about how a barometer works. So here it goes.
This program contains experiments which are performed by professionals. These tests are dangerous and may involve the use of hazardous materials. They should not be performed or imitated under any circumstances. The barometer. It has a pleated, a main indicator arm. That arm travels across the barometer's dial and indicates changing levels of atmospheric pressure. But there's more to the barometer than meets the eye. But to understand how it works, we'll just have to break it. First, the capsule. The aneroid capsule. It's just an empty metal can. Because it has little air inside it, it feels the force. The force of atmospheric pressure. And when that force pushes down on the capsule, it offers no resistance. The capsule contracts. When there's less atmospheric pressure, the capsule expands. On that capsule lies the L-shaped end of the lever. It attaches at the other end to a gear system. The lever follows the movement of the capsule as it expands and as it contracts. Except for one thing. Even a massive change in air pressure only makes that capsule move by 1/100 of an inch. The barometer is the lever and the gears each do their part to magnify that range of motion. First, the L-shaped lever. It has a shorter section that rests on the capsule, while the longer section locks into a triangular-shaped gear. Because of its greater length, it almost doubles the capsule's range of motion. And the lever transforms the capsule's linear motion into a rotational motion. Because the lever actions the gear very close to the gear's axis of rotation, it multiplies that motion up to 3 times more, and rotates the gear. Now, as that gear rotates, its teeth lock in and engage with the teeth on a second gear, shaped like a wheel. That wheel-shaped gear has a very small diameter, which, as it rotates, multiplies the motion another 18 times, and moves the indicator arm. And that's how a motion, that's so slight it can't be seen by the naked eye, is increased again and again until it turns into a visible motion. With that, the barometer is able to track changing levels of atmospheric pressure across the dial.
So this showed you how a barometer works nowadays. Now back to more simplistic devices such as the one you used at the lab. Well, actually I'll talk about those in a minute, or that one in a minute, but first there's another variation of the same thing here, except that here it's closed on one side. So we're not comparing the gas pressure based on the atmospheric pressure, but solely on the column of mercury in this case. So we call this device a manometer rather than a barometer. A barometer would really be measuring the atmospheric pressure. When we're measuring the pressure of a gas relative to something else, or nothing in this case, just the column of mercury, we call it a manometer. So here we have a vacuum, and what we're basically doing, we're taking a container with a gas, we're plugging it on the other side, and based on the pressure of the gas, the column of mercury will move. Upwards, obviously, because this here is exerting some pressure. Then what we will do is measure the height. How much did it move by? Because obviously, initially, it would have been leveled off on both sides. So now, it's at this level here and at this level here, the difference can be read on this scale, on this graduated scale. So they did the calculation for you here. They said the difference is 56 centimeters of mercury, which is really 560 millimeters of mercury. So that would be the pressure of the gas, 560 millimeters of mercury. We could convert that to kilopascal based on what I told you before. So 101.3 kilopascal is equal to 760 millimeters of mercury. But in this case, they didn't ask you to convert, so you could just leave it in millimeters of mercury. Next, we have something similar to what you used in class, except rather than having water, we have, again, mercury in here. So we plug the container of gas. This causes the column of mercury to move. Again, you can see here that the gas is exerting more pressure than the atmospheric pressure, causing the column to move in this direction. So they're giving us the pressure of the atmosphere, which is 760 millimeters of mercury. And the difference here is actually calculated again for you. It's 300 millimeters of mercury. So if the atmospheric pressure is 760 and the gas is stronger than the atmosphere by this much, that means the gas must have a pressure of 760 plus this difference, which was calculated to be 300. So the total pressure of that particular gas is 1,060 millimeters of mercury. Again, they did not ask you to express it in kilopascal, so you don't have to convert anything. In the last example, you will have to convert. So let's look at it. So we have here a gas, again, plugged here. Now we can see that the gas is not as strong as the atmosphere, as the atmospheric pressure, which is given to you as 102.6. So they want to know what's the pressure of the gas. Well, if we calculate the difference here, the difference is 370 millimeters of mercury. So the pressure, the atmospheric pressure, is stronger, because it's pushing harder, right? Stronger than the unknown gas by a factor of, or by 370 millimeters of mercury. Now in this case, they chose to convert the pressure in kilopascal here into millimeters of mercury because the device measures in millimeters of mercury. You could actually do the opposite. You could figure out this height and then convert it to kilopascal and then do all your calculations after in kilopascal. But we'll stick to this example. So what they did is the opposite. They took the 102.6 kilopascal, the atmospheric pressure, and they changed it here in 2 millimeters of mercury. So we know that 760 millimeters of mercury is equivalent to 101.3 kilopascal. If the atmospheric pressure is 102.6 kilopascal, what is the equivalence really in millimeters of mercury? So it's just a simple ratio. So they find that it's 769.8 millimeters of mercury. So that is the value of the atmospheric pressure. Now, knowing this and knowing that the gas is weaker by H, let's find the actual pressure of the gas. We had said that H had a value of 370, so it should be the atmospheric pressure minus 370 that will give us the actual strength of the gas. So you have the calculation here, and it gives you 399.8 based on significant figures. It gives you a final answer of 400 because you have 370, which has no decimal. And here we have one decimal, and because we're subtracting, we must keep no decimal, which changes 399.8 to 400. So that is it for that, and well, stay tuned for your next episode, 2.4.